through the linear classification task. Then after that, yeah, we'll show you guys the solution, and then we'll talk about the kernel tricks stuff. So let's. I firstly want to go through like some random stuff that you guys try to use to like tackle the bias problem. So one very common trick is that you guys like to multiply a constant onto the bias update. So let me just rewrite uh, the update part of the algorithm. So you guys do, so if the yi multiplied by xi theta plus theta naught is smaller or equals to 0, you'll do x. So the x update is normal. The theta update is normal, but then your theta naught is usually theta naught plus yi, right? But you guys like to multiply some very big constant here. Okay, so this kind of works. It allows you to converge pretty fast. But let's see why like this thing actually works, right? So if you write the equation of your classifier, so this is your decision boundary, and then we normalize both sides. Okay, so this is your absolute distance from the absolute distance between the decision boundary and the origin, right? So it's this distance here. And you realize that this distance is affected by this. So every single time you're actually updating theta naught, you're actually trying to sort of change the offset, this distance between the decision boundary and the original point. And you realize that because your yi is strictly -1 and 1, the update step that you guys can take is very small. Whereas the weights are getting larger and larger, right? Because your xi can, each coordinate of your xi is a subset of between -1000 and 1500. That's the data set I give you guys. So this is very big value. So your weights will get larger and larger, whereas your theta naught is not changing as fast. So every single time you update theta naught, the nudge that you give to the decision boundary to move it away from the origin is actually very small. So if you multiply a really large constant to it, that might work, right? That can make you update pretty fast. But there's a problem is if you consider a case where your x coordinates are very small, like very close to 0, so like -1 to 1, for example, and you still apply this really large constant when you shift the theta naught, your decision boundary will be bouncing around and sort of never converge. So this is not a very generalizable solution. It only works for a specific case where the bias is really large. So this is not a good solution to that problem. And then, so that's the one thing. I will show you guys how to do it properly later. There's another method which Billy uses, which is really kind of weird. I don't really understand it. So you first define an error term, which is, I guess, equal to this label minus this, if I'm not wrong. Okay, so this is very strange because your label is actually between -1 and 1 again, whereas this value is not constrained at all. It can be any value, right? So this is not constrained at all. So essentially what's happening for your x coordinate, which is really large, is that you're just taking this value here and then deducting it by a really large value. That's the output of your classifier. So your error is typically a very large value. And then in your update, your perceptron algorithm update, you're doing, I think, this plus the yi and then plus the error. So essentially your error term for a lot of the cases is going to be very much larger than yi. And then essentially you can ignore this term. So what's happening is that at first, your algorithm will be updating quite fast because your error is quite big due to the large constant here. But as time goes on, the norm of theta gets larger and larger, and then it becomes way larger than error, which renders it pretty much useless. So this update kind of works for the front part of training, maybe first few passes you make with the training samples, it kind of works. And after that, it's not really doing anything. So this is not really affected by any other samples because it only takes effect in the first few data passes. Okay, but it's not really a valid method to do this kind of thing. And then this error actually has a little bit of a different implication when you move on to hinge loss, right? So I give you that data sample where I think I have a point like this and a point like this and then a point like this, and then it kind of just doesn't work, right? Because the way you're updating bias is essentially you're plotting it by the DLD theta knot, and then you deduct it by the error. Okay, so error again is quite a large term. And essentially what's happening, if you are to visualize this, is that if I have a data point here, it's telling the decision boundary that it wants the decision boundary to be closer to itself. So it's going to pull it here. And then in a data set I give you guys, there's going to be very likely an equal and opposite point on the other side that says, okay, I also want a decision boundary near me. So it's going to pull the decision boundary toward itself. So essentially, these two forces actually kind of cancel out. So the decision boundary doesn't move that much. So it shifts by a little bit. So this method will work only if you have a very evenly distributed data set. So you have basically like 3 points on this side and you have 3 points on that side. Whereas the simple data set I give you, it does not have any other data point here to offset the large pool that's exerted by this data point. So as a result, the boundary kind of sort of never actually converges. And if you generalize this, the data set could look something like this with many, many blue points and just a little bit of this red point. So you see that these data points here with really large values, they're not like balanced by any other data points on the other side. As a result, your boundary would just be shifting around and it cannot converge. So this is not a valid method as well. And then the second method that you submitted, which is you simply remove the learning rate and you just update by DL d theta naught, is essentially the same as multiplying it by a large constant. Okay, so and I already explained why it doesn't kind of work. Okay, so those are the two methods that you guys try to make it work, but unfortunately, neither of them are very great. So we'll show you guys the correct way to do it later. But for now, I'll have Alistair just go through the markers report and some of the feedbacks that we want to give.
Can you hear me? Okay. Let me just.
Sure.
I'll just share screen. You all see this?
No, cannot see.
Yeah. Okay. Then you can see. Okay. So. Yeah. Similarly to the linear regression project markers report, we are going to go through the feedback question by question, right? So it is good to see that most of you all have heeded the advice from the previous project and are starting to work in object-oriented programming structure. And also we can see some attempts by you guys to exploit vectorization, which is the performing batch operations on the tensors so that you can speed up your training time. So the idea of vectorization is already inbuilt into the ML libraries, and if you want to truly understand it, you should know how to implement it by yourself. So for those that were still using for loops, for example, in this code sample here, the details of which you can read yourself in the markers report, then we strongly encourage you to basically use like the TensorFlow inbuilt functions to do batch reduce sum, reduce mean, etc. on the actual tensors themselves so that your algorithm isn't so slow. And anyway, as we mentioned, as I mentioned in the last markers report, your GPU is optimized for matrix multiplication. So if you are not doing vectorization, you're wasting your GPU. Okay, and here we again have a more detailed explanation for why it doesn't work if you use a large coefficient to amplify the updates to the bias. So you can read this if you want. East has already explained it, so you can either review the recording or go back here to read it. So what he didn't mention just now would be that because we already told you in the question statement, right, that the data is highly biased. So this is kind of a hint for you to perform some sort of scaling on the data so that it's more manageable. So recall from the very first things we asked you to do, right, which is the pandas course. There's one part of the pandas course, sorry, no, not the pandas, the Kaggle course that tells you that scaling is different from normalization, right? Scaling will change the range of the data, but will not change the distribution. Normalization will change both the range and distribution. So because we have a classification task here, we are concerned with the distances of the data from the decision boundary. So we cannot let the distribution of the distances for each feature. In this case, we have is a 2D case, right? So we have feature x1 and feature x2. We cannot change the distribution. So scaling is what we want. And so because the data is highly biased, and that's a bad thing, and therefore we want to make sure such that the magnitude of the raw coordinates, which is the points that's returned by a generator function, doesn't become a factor that decides your model performance. So in other words, right, we want to have a model that generalizes well. So regardless of the range of the data, it can still split the points correctly so that it won't break, for example, a series code if we put in data points that are close to zero. So the technique that Yiqin is used is a z-score. So basically each of the for each of the features, we have two features, right? X1 and X2. You perform this. You change every single observation into its corresponding z-score. So you just take the value and subtract the mean and you divide by the standard deviation. So this z-score gives you an idea of how many standard deviations away from the mean a data point is. So regardless of how big the spread of the data is initially, we can always reduce it to this more manageable range as dictated by the z-score. So that even if you have a very biased data set or one that is nicely centered on origin, your model can still handle it. And the last piece of feedback for question one would be uh, for those people that were kind of doing unnecessary transpositions of the matrix, unnecessary steps, we recommend that you make better use of like the library functions so that you don't kind of do extra work and do redundant steps. Okay. Now we move on to the hinge loss. So basically, almost all of you took your existing code for the perceptron and then you ported it over and you made some changes to implement the hinge loss. So this is correct because as Itzy mentioned in the lecture, the hinge loss is just an extension, an improvement upon the vanilla perceptron. So this is the correct move. But there's 2 points which we want to reiterate because these are the conceptual errors that were revealed in marking. So the first thing is that some people use different learning rates for tuning theta versus theta naught. And this is not good because it can lead to instability. For Marcus, from personal experience, he said the learning rate of theta naught to be 10. And sometimes his model will converge, sometimes it will just dance around 50% accuracy. So if you think about it, actually if you have a very big model that let's say has a million trainable weights, right? It's not a good idea to define a separate learning rate for every weight and every bias because then it will mean that you have a few million hyperparameters that you as a human have to decide, right? Then what's the whole point of machine learning if you as a human have to tune every single hyperparameter yourself? So that's why in machine learning libraries, you will usually see that there's only one learning rate variable to control the entire training. And this learning rate is used in each step of the backprop to update each respective weight and bias. Okay, and the second point would be that the hinge loss is continuous. The values that it outputs are floating point; they're not discrete. And this is because in the formula, right, if the point is misclassified, we output 1 minus the prediction, so that the closer the point is to the margin, we get a 0 contribution to loss, and the closer the point is to the decision boundary and is wrong, then we get increased contribution to the loss. So this means that we are tuning the weights we're tuning the boundary in accordance with how close they are to the boundary as well as how wrong they are, so that we can get those nice margins, right? So this is an improvement upon the vanilla perceptron, which only gives us a sign, which is whether it's correct, that means the signs match, or it's wrong, that means the signs don't match. That's why you get negative value. And therefore, right, because the hinge loss is continuous, we shouldn't see people summing the signs or just directly taking the signs to be the output of the hinge loss algorithm, because it's meant to be continuous. So yeah, this is the second point. And lastly, because we have two parameters, the learning rate, because this is a gradient descendable problem, and the second one being the regularization hyperparameter, these are two things that the programmer has to decide. So we highly recommend that in future tasks, well, anyway, this will be like the last assignment where you will have to derive something from scratch. So in future assignments where you use libraries like keras, etc., we highly recommend that you exploit their functions to split the data into train, validation, and test sets. Etienne has already mentioned what these three things are in the previous lesson, because the validation is especially useful for you to decide on good hyperparameter values. Anyway, in ML competitions, at the top, the defining characteristic will be like those few percentage points that you can gain to get an advantage over the other teams, right, and improve your ranking. So hyperparameter selection is what will give you that extra percentage points. So that is why it's very important for you to know how to split train, validation, and test sets, and do your optimal hyperparameter selection. Okay, the last thing would be the extra task, which was to visualize the data points. So in order to do this, you would have to use the Cartesian form of the vector equation, which is actually inside the drive. Is inside the excerpt from the chapter 7 math notes that are uploaded. So for those who implemented that, good job lah. And for those who didn't, just remember that in practically every ML task, you would always want to kind of visualize your predictions to tell if your model is doing nonsense. For example, natural language processing, you want to visualize if you pass in some example sentences, if you have a sentiment detector, whether it's giving you a nonsense sentiment. If you have object detector, you want to see if it's drawing the bounding boxes correctly, etc. And that is why this task exists. But as an FYI, in more complex models like neural networks, usually people when they try to visualize things, they visualize the outputs. They don't visualize the actual weights of the model itself. Unlike what we're doing now, because we only have one data and one data node, so it's very easy. You can just directly use that to plot graph. But in more complex models, you don't want to do that because the weights are only understood by the model. It's all gibberish and numbers to humans, and that's why it's only meaningful to output the model predictions. Yeah. So that's the Marcus report. It is inside
Is
the
it, is
drive.
it,
Yeah.
sorry.
Yeah.
Is it possible to search for hyperparameters algorithmically, like do binary search or something for the correct learning rate or
Yeah.
like
So
Yeah,
verticalization?
this thing called quick search.
yeah, there are actually many hyperparameter
Yeah, this thing called quick
search
search.
hyperparameter search algorithms available online, and also on GitHub. You can just like script kiddie and use them. I actually have notes for how some of them works, but I cannot remember on the spot now. So if we do go to that stage where we share with you, then we can always hold a lecture. If not, I'll probably just refine those notes and upload them as extra material into the ML curriculum.
Alisa, can you like explain a bit like what do you mean by like a bias data set? Like what sort of bias? Because
His
I don't quite understand how like if you just like reduce the magnitude of the number can solve the problem.
okay okay highly biased in this case. If you remember the generator function, his weights was 2, 3, right? And his bias
Yeah,
was 2000.
yeah.
So that means that okay, for his generator, his x values were generated from a uniform distribution, and then he sampled from negative 1.5k to 1k, right? So this will mean that the x values come from a pretty wide range. But because of the bias of 2k, right, it means that you're kind of displacing everything like a huge distance away from the origin. Because you plus the theta naught, right? When he generates the y, you take x dot theta plus theta naught. So you plus 2000 means everything is going to get shifted by 2000. Okay.
Wait, so how does like making
yeah.
it like how does making a number like of less like a magnitude actually solve the problem? Because
Okay,
the distribution like is still the same one. Like
Okay.
the relative distance from the origin.
So so basically that's the answer to that would be like this huge chunk of text. Basically, like because remember this is our plane equation, right? And if we move the theta naught to the other side of the equation and we divide by the norm of theta, then we get perpendicular distance from boundary to origin from the line. You agree? Negative theta naught divided by norm of theta, right? So because in this case the data points were biased like to like 2000 away from the origin, it means that a lot of them are far away from the origin, and it will be natural, therefore, that when you train, the magnitudes of the weights are large because you are essentially doing repeated vector additions, right? To shift your normal of the decision boundary. So because the magnitudes of the norm of each of the data points is large, that huge those huge numbers will kind of also get propagated to your weights, right? And now here's the problem. Your weights are large means that your denominator here, the norm of theta, is going to be large. So if you guys put a huge constant in front of your theta naught, you have a huge number at the top, you have a huge number at the bottom. End result, it's still roughly okay. It's still roughly okay. It may or may not be able to approximate 2000, which is why, for example, some of you can put like maybe 10,000, 100,000 in front of your bias when you're making your updates. But somehow, even though your bias ends up becoming a few million at the end, you can draw a nice line. It's because when you actually consider the perpendicular distance from the boundary to the origin, you have a big number on top, that is your huge theta naught, and you have a big number on the bottom, that is the huge norm of your weights. Because the norm, remember the norm of the weights, the L2 norm is the Euclidean distance. It's basically just the application of Pythagoras theorem, right? So that's why it can approximate 2000. Then if they are pushed close to zero, if you feed in a data set that is pushed close to zero, then this thing just dies out because like your theta naught is big, right? But your norm of theta is small. Then you get a problem, cannot converge. So what happens when you scale the data to the suitable range? That means that before you even train, you already scale to that nice range from 0 to 1. Then it means that no matter what the starting range of your data is, at the end, right, it's always going to get compressed to 0 to 1. So that is why we eliminate the fact that the magnitude of the raw coordinates may be able to decide our performance. So no matter what the initial magnitudes are, we force all of them to be in the range 0 to 1, in this case using the z-score, or there's other kinds of scaling. You can always use other ones to find online, and if they make sense statistically, then it means that before you even start training, you already have a nicely scaled data set, and that will mean that you can train stable values of weights that are not insanely huge, like 875 or like 600 plus, and that will also mean that your value of theta naught need not be prefixed with a huge constant, and you can get close to 2000, which was what was initially put inside generator.
So instead of trying to approximate the raw bias, you try to approximate this z-score.
No, you're still approximating bias, just that the bias actually now after scaling is really, really small, and I can show you that later.
Yeah, so basically by using the huge constant method, right, you are kind of getting a fluke solution.
But like if you like scale the entire thing down, right, then won't they also make the weights like even smaller than before?
Yeah, but the ratio is correct.
Yeah, the weights will be very, very small, but that's a good thing, right? Because ultimately, you also want the weights to be small. You want to make unnecessary adjustments to the weights because currently, if you don't scale it, you're gonna get like freakishly large weights, which is not really very friendly to deal with. But then after you compress it, you actually just localize everything to near zero, and that will just make things converge way faster.
Actually, another important application of scaling to the range 0 to 1 is also evident in computer vision applications, and we will go through this later. But realize that whenever we do CV, we pass image into convolutional neural network. We don't use the raw values of the pixels. We don't use 0 to 255. We always compress it from 0 to 1. And this is also for the same reason, to prevent instability. And also with smaller values, your the number of train steps that you need to take decreases, because then your partial derivatives won't be so messed up.
Okay, I guess we'll just go through the solutions now. See some
Yeah,
code.
okay,
Yeah.
I stopped sharing.
Wait, sorry. Can you give us a few minutes because we are chased out of our classroom?
Okay.
And where are the
Okay.
rest? Can we go and look for them? Hello, people.
Yeah.
We are
Are
like
you?
cafe. Yeah.
Oh, we go there and look for you. Thanks.
Outside
What?
the cafe.
Okay, okay.
You wanna wait for them first to move?
Yeah, I'll wait for them.
Okay, meanwhile you all just take some time to digest. Or I will post the link to the Marcus report in the chat and you all open it and review.
Wait, so what you transform the data so that instead of like wait, what how does the Z score factor into this again?
So basically, what you can think of it as a way to compress data. So currently, the generator is outputting data between data points, x values between negative 1,000 and 1,500. So what it's doing is taking that same distribution, it just decrease the magnitude of all the coordinates and just compress it down to a very localized set of data that's near the zero, that's near the origin. Yeah, that's all it's doing.
Wait, actually, okay, to be more precise, right, what I mentioned earlier about the z-score ranging from 0 to 1 is actually wrong. It should
But
be
mean is
centered at
zero.
0. Yeah, it should be centered at 0, and in the positive and negative direction, add 3 standard deviations. So that is the range that you compress the data to.
But then for this one, like can I also use like the min-max scalar from a scalar and then just make it 0 and 1 as a boundary? Like
Min-max might change the distribution.
it just like find the largest and the smallest number,
Yeah, yeah, I know.
and then make the largest one and make the smallest 0. Then like you scale.
Actually, no, that's scaling. That's scaling. It should be okay. It
Okay.
doesn't change it. As long as it doesn't change the distribution, it's okay, because it's a distance dependent kind of statistics.
What's an
Application.
example of a method that would change the distribution?
Oh, actually, it was taught in. Yeah, you can. There's one inside the Kaggle course itself. It was. Yeah, I remember. Let me just go back there again. Actually, I went through this in the first ever lesson, but I think everyone forgot. I also kind of forgot. So Okay, Box-Cox transformation. That's the name. It uses a log graph.
Oh.
That's why it matters. Yeah. Okay, it was under the data cleaning course, and the second lesson in there is scaling and normalization. Yeah, the box course. Yeah, the box course one will force it to change into. It will force it to change into a normal distribution, because it uses a log graph. You know that log graph, right? For values that are from close to 0 to 1 range, the log graph, right, changes values very quickly, and for large values, the log graph doesn't really change the y value a lot. So that's the reason why you can kind of have a non-uniform penalty that you apply to each data to kind of force the distribution to change.
Wait, so they're there already, right?
This one they completed like in week 1.
Okay, wait. Okay, since everyone's here back, I'm just gonna go through the solutions. Okay. Okay. Okay, everyone can see, right?
Yeah, can.
Okay. So okay, let's just go through step by step. So importation. Okay, this is a gen function that we used. Here's the way that I did a boundary plot. So essentially, I have all these parameters that allows it to be more generalizable. So I first get the data set that I want to plot, right? So the x and y, a, b, and c's are your basically parameters of your model. And so I'm gonna get I'm gonna separate the data into the 2 different classes. Here's what it's doing. And then I scatter plot them so that they can be of different colors. And then I essentially use this numpy function to generate random points, basically points along the x-axis, 100 of them. So I can use this to plot a line. So to get the y coordinates from the x coordinates, I'm gonna use this equation, which is basically your Cartesian form. Okay, so you apply this and you plot this, and then they will give you the plot. Okay, so this, most of you already know how to do this, so there's not much problem with this. Just take note that this actually is one of the vectorization methods that you might want to apply when you're trying to select all the wrong samples and all the correct samples. So you don't actually have to for loop them individually. Instead, you can use this, just get all of them at once. So I create a generator. So for the perceptron, I'm just training on a small set. Mostly because if I increase this number to like even bigger, you probably just can't see anything on the plot. It's just gonna be 2 colors, which is not very useful. So this is a pretty good number that you can still see the data points. And okay, I plot it using my plot function here. So here's my parameters for the decision boundary, 2, 3, and 2000, right? And then it'll look like this. So from this, you can see that the decision boundary is shifted pretty far away from the origin. So the perpendicular distance here is actually about 500 plus, 555, something around there. So it's quite far, okay? And then we'll see a different plot later after we normalize it. So here's a perceptron class. Let's talk about initialization first. So because the perceptron needs to be generalizable to any dimension, so here's an input for the initialization, which tells you what dimension it is. And then you can simply initialize your weight using this dimension. All right. So, and theta naught is always a scalar, so I just initialize that to 0. Here's a scaling function, which Alistair just talked about. So essentially, we're finding the mean of the data set that we're training on, and we're finding the standard deviation of the data set that we're training on, and then we simply normalize it. I'm also storing this as a property of the model itself, because we need to apply the same set of pre-processing to all the other data points, the validation data points and the testing data points. So we need to store these values for use later. Okay, and this also sort of tells you that you kind of need a pretty representative training data set, because if your training data set too small, then your normalization method will not be very generalizable to validation set or the test set. Okay, so I'm gonna skip these first and go to train first. So because the perceptron algorithm needs to see the same data points multiple times, so for this training, I'm actually just training on the same set of sample. I only generated samples once. So this is the x and y. And I store a skilled version of the dataset just for plotting. So I store these two for plotting purposes. You don't actually have to do that. Okay, then I'm using epochs and steps, but it doesn't kind of make sense for this case, but we just deal with it for now. So epochs and steps. Here's how I compute the agreement. I'm using this predict function and multiply by the ground truth label. So let's look at predict functions first. So it takes the input, this in the training set, so this training set, and then goes into predict function. I'm going to scale this first because all the data set that we see in the model must be scaled. So they're scaled to the same mean and the standard deviation that we just calculated. And then here, because remember the X is actually a batch of data, so it's this entire operation is vectorized. So what I'm doing here is essentially the formula that I showed you guys, just vectorized. So I'm reducing sum on the last axis, which is, so in this case, it's batch size by 2, right? The dimensionality is 2. So reducing sum on the last axis will just create a resulting tensor that's length of the batch size, right? And this is the formula that we showed. And then you plus the theta naught, and then you only take the sign because this is the perceptron algorithm. Okay, so the output of predict is just the sign. And with that, you can compute the agreement pretty efficiently because the whole thing is vectorized. And then gathering of the wrong samples and the x-axis, the x values, data point values, and the labels. So I'm using tf.where. So I'm comparing to see where our signs are smaller or equal to 0, which means that it's wrong, right? And then I simply gather all the corresponding values from the training set with the identified indexes. And then they will return all the wrong samples. And I'm doing the same thing for the Y samples. I'm just expanding the dimensions so that the shapes will be compatible later. So in this case, this should be 640 by 2. This should be 640 by 1. And percentage error, very easy to calculate with this too. You can just take the length of one of these samples and then, yeah, divide by the overall length of your data set. That will tell you the percentage error. Okay, so because now we also have these two vectors identified, the weights update is also very simple and very efficient. So we simply take the wrong samples x and multiply by the wrong samples y. That will give you the update that you need for the data, the weights. And for bias, it's just wrong samples y, right? So this is the way to vectorize your entire operation. So there's no for loop involved for tuning, right? And what is this? Self.step. Okay, that's just the same. Yeah, that's just update. Okay, so after that, I print error, and then because the perceptron learning algorithm is by right supposed to be able to linearly separate this data, and it actually does it pretty fast after you scale your data set. So I'm just gonna stop the training if the error is 0. Okay, that's just simple stopping, early stopping. And here's the training. So the error rate is generally quite small already when it starts out, and it converges pretty quickly. And here's the graph that we plot. Okay, so here's the weights that we got in the end. So you see that the weights are quite small, and actually the weights are normalized. So this is one way for you to directly compare weights and see if it's correct. So if you just normalize 2, 3, 2000, you'll also get the same set of values, except for this. This will be different because we scaled the data set. So the weights, normalized weights for 2 and 3 should also be like this. And in this plot, you can see that the value range is very small. It goes from -2 to 2, and then yeah, so basically quite small, very close to the origin. And you realize that the actual offset from the origin of your data boundary after you compress the data is just 0.39. That is quite small, way smaller than 2000. So that makes it really easy for your training algorithm to converge on this value. It doesn't need to update that much. So that's why you should be scaling your data set first. Okay, so that's for the perceptron algorithm, pretty simple. Hinge loss will be very similar as well. You have the same set of scaling functions. Initialization, you need a little bit more stuff. You need the learning rate and you need the regularization term. Okay, so the rest is the same. Predicted function will be slightly different. You're still doing the scaling, but instead of returning just the signs, you're returning the values now. Okay, so you're not signing this expression here. Stat will be kind of different because now you're doing gradient with the learning rate. Okay. And okay, loss, we'll talk about this later. So let's just go through the training and do the one by one. So because this is actually a model with hyperparameters, you kind of want to use a validation set to sort of try to select your regularization term or learning rates and stuff like that. So this is why I first generated the data set, and then I select a portion of it, in this case 25%, to be the validation data set, and training data set will be the rest. Here's the, because we have two data sets now, I'm going to scale by the training data set. And then I'm going to, because the training, the scaling function actually stores the data mean and standard deviation, I'm going to use the standard deviation and the mean of the training data set to also scale my validation data set, because we want to use the same pre-processing methods for whatever data sets we want to use. Okay, I'm going to store these two just for plotting purposes. Okay, again, you don't have to do this. So here's a really short code for training. Epochs and steps, and then after that, you're using the gradient tape, you're going to make some predictions, and the prediction goes into the loss function. So we take a look at the loss function. So I first create a bunch of zeros, because the loss function takes the maximum value of 1 minus your prediction multiplied by the label, and also a 0. So this will just help me vectorize the entire thing. So this entire expression here is essentially that loss that we showed, hinge loss. And then after that, you add on to, you mean this because you have multiple data points in a training set. You mean that, and then you go ahead and add on to it the regularization term. And remember, you need to square this term. A lot of you didn't square this term. So that is just a simple computation of the loss, and then we can return it. Okay, so the whole entire process is vectorized. And after that, we compute the validation loss using the same set of procedures. Okay, so very simple. You predict and you put in the loss function that will give you the loss. And then I'll output both the losses at the same time. So I'm still using 640 data points, although it can deal with much larger. I've tried 6.4 million, it works fine. But you can't see the data points in those cases. So here's the parameters that I basically chose. I just quickly tested a little bit and I found this to work pretty well. And then we can train on that. And then the loss can get onto a single percentage, which is pretty okay. And then from here we can plot both of the sets. So for the training sets, training set, it looks like this, and for the validation set, it looks like this. Okay, so it generalizes pretty well. And yeah, that's basically it for this entire task. So it's not too difficult as long as you scale your data set. So I hope you guys now know the importance of data preprocessing. And so that allows you to just do your stuff very simply instead of having to use really hacky and weird methods to play around and deal with a really high bias data set. Okay, so this is definitely one important skill you want to apply for other tasks. And yeah, I'll be uploading this onto the drive. So if you still need to clarify the code, you can just go up there and look at it. So far, any questions? If not, we'll move on to today's lesson.
Wait, I got one question. Just now you use wait, can I move to your arrow part?
Error? Here?
Loss, sorry, I mean loss.
Loss?
Yeah, can I replace the zeros with the number 0?
You can try that. I think it should work as well. I think it should work as well.
Okay.
Yeah, just a small problem there. Yeah, okay. Okay, so no other questions? Okay, no other questions, then we'll move on to today's stuff. So today's stuff might be a little bit confusing, but luckily you guys don't have any tasks to do for that. But it's still a pretty fundamental concept to sort of try to understand.
Wait, sorry, here's a cue to pause the recording and start a new one.
Okay, actually, do you want to take a break? 10 minutes? Because we've been talking for quite a bit.
Can also.
Yeah, okay, maybe we just take a 10-minute break first, then we come back and do this. I'm gonna get some water.
By the way, how many of y'all look at the SVM stuff inside the pre-reading document? Wait, never mind. I think people zao already.